I'm Christine Joyce Gante.
I'm Venice Perlado, and we are going to present our thesis entitled Fabrication and Characterization of Acetic Acid Treated Salago Fiber Reinforced Epoxy Resin Composite. Salago fibers is a type of shrub that has extraordinarily high fiber potential and is usually used in manufacturing banknotes or paper money.
So here's the objectives of our research. To maximize the strength of the fiber to matrix bonding, to use glacial acetic acid for the chemical treatment, then use sodium hydroxide as a neutralizing agent, and to know the effect of the treatment to the properties of the fiber.
So why are we doing this study? Few researchers use Salago fiber in composites as filler or reinforcements. No study has been done wherein Salago fibers are pre-treated in glacial acetic acid and neutralized in sodium hydroxide. Only few studies has been done wherein they vary the concentrations of acetic acid solution.
So for our scope and delimitation, this study will cover synthesizing pre-treated Salago fibers with glacial acetic acid reinforced by epoxy, characterizing the composite to observe the effects of the chemical treatment that involves SCM, UTM, FTIR, TGDTA, and impact tests. Although this study will not cover possible applications for the treated fibers.
For our methodology, the materials that we used are the following. Salago fibers, glacial acetic acid and sodium hydroxide, epoxy resin and hardener, negative and positive molds, and RTV silicone food grade.
So for the fiber separation and treatment of our research, first we're going to use water resin. Salago barks will be submerged in distilled water for 1 week. Then next is air drying. The fibers will be separated manually and air dried for 2 weeks. Then chemical treatment, wherein the fibers will be soaked in 1, 5, and 10% acetic acid solution for 2 hours and neutralized with 0.1% sodium hydroxide solution for 1 hour and rinse using distilled water. Lastly, air drying and sun drying. The treated fibers will be air dried for 2 days and sun dried for 5 days.
For our sample preparation, we cut and placed the fibers into the molds and used a 5:1 ratio of epoxy resin and hardener to cover the fibers. And then we cured the composites for 3 days. For our experimental design, so we only focused on treating the fibers in varying concentration of acetic acid solution with a fixed weight percent of 15%. And then we used FTIR, UTM, impact, TGDTA, and FISM as the characterizations of the composite and fibers.
So the characterization that we use in this study are universal testing machine, field emission scanning electron microscopy, Fourier transform infrared spectroscopy, thermogravimetry or differential thermal analysis, and isode impact tests.
We will now proceed to the results and discussion of our thesis. So for the first part, we have the FTIR results, and these are the treated fibers that were submitted to DOST last year. As we can see in figure 2, this is the FTIR spectra of the 4 samples. So for this part, it ranges from 3,287 to 3,339 per centimeter, and it shows the absorption band for intermolecular hydrogen bonding. And we can see as the concentration increased, we can see that there is a decrease in peak in this area. The amount of hydroxyl groups decreased, which indicates that the treatment had successfully removed the hemicellulose and lignin content of the fiber. At 2,918 and 2,852 per centimeter, the CH stretching of hemicellulose can be seen as 2 shoulder peaks.
So at this peak, which is 1,736 per centimeter, it is believed to be C double bond O stretching of acetyl groups present in the hemicellulose. As we can see in this figure, we can see that the acetic acid treated fiber showed a decrease in peak compared to the untreated one, but only peak compared to the untreated one, but only up to 1% treatment concentration. But based on this figure, there is an increase at 5% and 10% acetic acid treatment, which can possibly be due to the removal of some components where the fibers has been treated. For the next peak, which is at 1,622 per centimeter, it can be associated for the water content, lignin, and hemicellulose. The peaks at this area also decrease up to 1%, but only increase when the fibers are treated at 5% and 10% solutions.
At 1,504 to 1,500 centimeter per centimeter, we can see the aromatic ring C doubles bond C stretching. We can see that due to the treatment, there is a reduction in the hemicellulose and lignin found on the Salago fiber. There was a partial removal of amorphous regions on the structure of the fiber due to the shifting of the peak to a higher wave number.
So the peak found at 1,028 per centimeter, it shows a CO stretching of the hydroxyl groups, and it did not show any change. And for the last peak, which is the 897 per centimeter, it decreased until 5% acetic acid treatment, but there's a significant increase at 10% because of the formation of the CH bond, and it is also associated to the CH bending of the cellulose and hemicellulose.
So based from the results, we can say that the hemicellulose and lignin content of the fibers have been removed, but up to a certain percentage only. It can be said that 5% treatment showed the best result based on the consistency and the decrease of the peaks, since the hydrocarbons at 2,918 and 2,852 per centimeter for 1% are still intact compared to 5%.
So we will now proceed to tensile test. See in the figures, as the treatment concentration increases, the tensile properties increases as well, up to 5%. We can see that 5% has the highest result, which is 83.6 megapascals at tensile strength and 8.01 gigapascals at tensile modulus. For the lower result in the tensile strength, untreated has the lowest one, which is the 72.4 megapascals, and the lowest one in the tensile modulus is 1%, which is 5.69 gigapascals. So based on the data gathered, 5% has the best concentration.
So from a research work where Napier fibers were treated with acetic acid, it showed that the tensile properties of the treated ones were higher compared to the untreated. The same thing can be seen here. The same pattern can be seen from our results. And it indicates that the fibers get closely packed because of the removal of the hemicellulose caused by the treatment. This could also imply that there is a good interaction between the fiber and the matrix, where the matrix directly bonds with the denser cellulose. So from the FTIR a while ago, we have seen that the 10% concentration had the highest removal of hydroxyl groups, especially at 3,350 per centimeter. But it doesn't imply that the hemicellulose and lignin were removed because it contains more hydrocarbons than the 5% treatment.
So we will now proceed to flexural test. Based on these figures, the untreated fiber obtained a better result in flexural strength and flexural modulus. The presence of amorphous phases could be the result for this one. As you can see, the untreated fibers in flexural strength and flexural module has the highest numbers, which is 79.4 in strength and 4.05 in modulus. For the treated fibers, 1% has the lowest data, which is 3.11 in flexural modulus and 61.3 in flexural strength. And the highest one is 10% in 10%, which is 3.49 gigapascals, and in flexural strength, 73.1 megapascals. 1% has more of amorphous phase than 5%, but the flexural properties are lower due to this synergistic effect. In terms of consistency in removing hemicellulose and lignin amorphous phases, 5% has the highest tensile strength and modulus because based in this tensile test, surface functional groups of the treated fibers play a role in resisting the pulling force applied. However, based on the FTIR results, even though 10% had the highest percentage of removed hydroxyl components of 3,000 per centimeter, it still has a considerable amount of hydrocarbons, which indicates the presence of amorphous phase. This might also be the reason why the sample with the untreated fibers had the highest flexural properties.
For the impact test, we can see the data in figure 5. We can see that 5% had the highest value for its impact strength. The untreated has no interaction with the cellulose because it is fully covered with hemicellulose. 1% had lesser amorphous phases, but it interacted more with the cellulose. This is 5% had the best interaction of cellulose and matrix, which resulted to a better impact strength. But the decrease in the 10% in its impact strength can be due to the presence of more amorphous phases where there is less interaction between the epoxy and the fiber matrix, as we have seen from the FTIR results a while ago. The treated fibers had better strength and is supported by the FTIR results where more hemicellulose component was removed.
So now we will proceed to scanning electron microscopy. As we can see in this figure, the 5% treated fiber composite are more bounded and held together by the epoxy compared to the untreated one. The interstices or spaces between the fibers are more penetrated by the epoxy matrix, which makes the interaction between the fibers and epoxy to be more effective. This can be supported by the results from the tensile and impact test, which showed that the 5% treated composite had the highest result. We can also see that there are fibers that were left and not cut off, which indicates that there is an additional resistance of the fiber caused by the good penetration of the epoxy polymer to the fiber and adds to the toughness of the fiber as well. It can also be seen that the bundles of the fibers are denser compared to the other concentration. For the 10%, the fibers are loosely bounded and the treatment is said to be effective. But when it comes to performance, it leads to more fiber pullouts or holes, which is caused by the decreased interaction in the cellulose. It can be suggested that at 5%, there is a good interaction between the polymer and fiber matrix because more cellulose component is present.
The untreated fibers have smoother surface than 1% and 5%. 10% has a smoother surface compared to G and F. And there are fiber pullouts, as we can see here, which indicate that the epoxy did not penetrate well and the fibers were easily removed. 10% can be seen that the fibers were denser compared to 1%, but here we can see that 10% is denser compared to 1%, but this is possibly because of the low magnification of SEM, because here at higher magnifications, there is no interaction with the epoxy. Lastly, for the TG-DTA,
as we can see at the first curve of the untreated fiber composite, it is lower compared to the treated ones, which indicates that more volatile components were removed. The curve improved and volatiles were lessened when the fibers were treated and the amorphous regions were removed. In terms of the decomposition or degradation temperature, there was only a slight difference where it did not only change in all samples.
So in conclusion, we can say that Salago fibers with 5% treatment of acetic acid solution showed the best result compared to the other ones in terms of its mechanical and thermal properties. From the fracture morphology in SEM, it also showed that there was a better adhesion between the fiber and the epoxy resin and through the treatment done in the fibers. Other composites also showed an improvement compared to the untreated one, implying that the treatment done on the fibers did improve its characteristics.